in a video. Probably shouldn't because I got other things I got to get done. But anyway, today did post a Feynman video. It's got actually another one I haven't seen yet. But anyway, I thought I would do the, where he disposes of the Lesage theory. I thought I would play that clip in response to this clip. So I'll play this first and just make my commentary on why this is just not a very good, this isn't a very good attitude for a scientist.
There's still a school of thought that cannot believe that the atomic behavior is so different than large-scale behavior. I think that's a deep prejudice. It's a prejudice from being so used to large-scale behavior. And there.
So that, yeah, well, the counter-argument would be, I'm rubber, you're glue. Yeah, there you go. How's that? I think it's obvious that you're the ones who have the prejudice looking for the thinking that it's bigger and better.
We're always seeking to waiting for the day that we discover that underneath the quantum mechanics, there's some mundane, ordinary balls hitting or particles moving and so on. I think they're going to be defeated. I think nature's imagination is so...
Nature's imagination. See, I mean, that sounds like a religion to me. And in another clip I heard him say God a couple of times. But, yeah, nature's imagination. So in every other respect, we find out that things aren't so magical. We have emotions and we think, oh, we're having feelings in our heart. And then we find out our heart is just a muscle that pumps blood. No magic. I could go through the list of things where it seems like, wow, that's really something, and then we find out, oh, there's an explanation. And the explanation is mundane in physics.
So much greater than man's, she's never going to let us relax.
She's never going to do it. So this is this whole attitude, like, yeah, what he's really saying is I've thought about it, and I've tried to do it, and I couldn't do it, so you can't do it, so give up on it. That's all he's saying. So anyway, but then that sounded a little bit, a little bit like a religion, right? She, Mother Nature. Yeah, she's just so clever. Come on. It's a little bit embarrassing almost. Anyway, so let's do Feynman on gravity here. Where the hell did it go? Feynman gravity. That's not the right page. I have it here somewhere. Where the hell did it go? Must be here. Just must be hiding. Yeah, it's over here, hiding from me. Alright, so this is where Feynman, in the oldest lecture, talks about the Lesage theory. I'm going to try to find some other lecture where he mentions it. But he is actually mentioned in, I think, the Wikipedia page for the Lesage theory as one of the people who was a detractor or a prover of its functionability or something. So anyway, let's play along again.
Now, if we take, on the other hand, Newton's law for gravitation, which has these aspects which I wrote down last time just to impress you with the speed at which mathematical symbols can carry information. We said that the force was proportional to the product of the masses of two objects and inversely is the square of the distance between them, and that bodies react to forces by changing their speeds or changing their motions in the direction of the force by amounts proportional to the force and inversely proportional to their masses.
Right, so basically it's this idea that as you go twice the distance, you lose 4 times the force. So it increases and decreases by a factor of 2 over the distance, or 4, in terms of divided by 4. So you just divide the force by 4 as you go twice the distance. That kind of thing. I mean, I never say it quite right, but I think that's accurate enough.
Now
Again, it's the same effect as this hand goes twice the distance. It's now 4 times as strong. The force would be 4 times as strong here as it is here. That's the idea.
Words, all right, and I didn't have to write the equation, but nevertheless, it's kind of mathematical, and we would wonder, how can this be a fundamental law? How can this planet out there look, what does it do? It looks at the sun and it sees how far away it is, and it decides to calculate on its internal adding machine the inverse of the square of the distance, and that tells it how much to move. This is certainly no explanation of the machinery of gravitation. So you might want to look for...
Right, so he's making a joke there. Nobody laughed this time. It's the same joke he made in another video. But anyway, yeah, obviously, there's a reason, there's a cause for the effect. And people want to leave the cause unknown. And I think it's knowable. I think it was known 200 years ago. And Christianity, quantum, decided to basically shut up anybody who dared speak the heresy. And it pretty much looks like that's all that's happened here with physics. It decided to kill the heathens.
Further. And various people have tried to look further. Newton was originally asked, it doesn't mean anything, it doesn't tell us anything. He says, it tells you how it moves. It should be enough, I told you how it moves, not what. But people are often unsatisfied without a mechanism, and I would like to describe one theory which has been invented for, among others, of the type that you might want, that this is the result of large numbers. And that's why it's mathematical. And I give this theory, perhaps you've thought of it yourself. Every once in a while, some student comes running in and he suddenly explains gravitation.
Yeah, well, see, I meant kind of again, just kind of a glib, like, okay, yeah, sometimes an Einstein sitting in a patent office, but actually he got some stuff wrong. Yeah.
Suppose that in the world, everywhere, there are flying through us at very high speed a lot of particles that come equally in all directions. They're just shooting by, shooting.
Right, so now he said very high speed. Now, why couldn't he just say the words at the speed of light? And then he might have understood this concept better. But it's just this idea, so he says high speed, as if he doesn't know what a photon is. Right? I mean, gravity moves at the speed of light. That he knew at this time, okay? He knew that gravity moves at the speed of light. So he already knew that connection. So why wouldn't a theory about gravity, why would he say moving at a high speed? Why wouldn't he say moving at the speed of light? Because it is sort of important. I mean, it has a consequence in the idea that nothing can move faster than the speed of light. So obviously the force applied would have an effect. So I guess this context also I'll say now, you know, Feynman knew, I mean, he's a great physicist, no denying it. But I'm just saying he knew this stuff, and he, you know, like I said, I'm just saying this is the hatchet job. As I'm saying, he didn't apply his knowledge to this problem. He just wanted to dismiss it, and he dismissed it casually. Because Feynman kind of knew this fact, right? And this is a fact that's going to have to, it would make you think. It's one of those facts where you say, I have to think about this. All right, the force of gravity applies a pressure of 16 feet a second. So every second it accelerates you another 16 feet a second. But what if your velocity is already 200 feet a second, right? So you're thinking of something going 200 feet a second, and I'm going to interject, and I'm going to push it 16 feet a second. Obviously, my push is never even going to affect it. It's going to be gone before I wave my hand to push it, right? It's going to escape my pressure. So how does a mundane pressure of 16 feet a second, how does that get applied to something that already has velocity? And of course it does. It just keeps adding up. So if you're going 200 feet a second, you're going to go 216 feet a second the next second. And onward and onward, and it's just going to keep increasing. So how is this force being applied? How does it get added on when you can't push it on, you can't wave it on? So that should have made him think a little.
By, shooting by, and once in a while hit in a bombardment. But we and the sun are practically transparent for them, nearly. But some hit, and so it's not completely transparent. Then look what would happen. If the sun is here, and the earth is here, then if the sun weren't here, there would be particles bombarding from all sides, giving little impulses by the rattle of these bang, bang, the few that hit.
Yeah, there's another thing where he, you know, Lesage's theory wasn't isn't unknown by Feynman by this time, right? So, I mean, I think he could have gotten it right, unless he should have just said a proportional density of pressure from all directions. Could have said that instead of making it sound scattered and inconsistent. It's a consistent pressure from all directions.
Which would not shake the earth in any particular direction, because there is many coming from one side or the other, from top, from bottom.
There, see, he knew it. He just didn't say it that way.
However, when the sun is here, the particles which are coming in this direction are partly absorbed by the sun because some of them hit the sun.
Right, so now he uses the word absorbed. Now, you know, we already know that there's lots of photons that aren't absorbed by matter. They go right through it. X-rays, lots of things go right through lots of kinds of matter. And undisturbed, unmolested. Lots of transparent substances. The screen I'm looking through has transparent substances through which certain photons will go right through it. Well, they don't technically do that, but anyway, let's not get into that. But there's lots of things that go right through stuff without getting molested. Lots of radiations.
And don't go through. Therefore, the number that are coming from this direction toward the earth is less than the number that are coming from the other side, because here they have no opposition from no sun there.
Right, so this is the basic theory, that there's a shadow cast by both objects on the other object. So this one has a very small, right, be just a tiny little shadow on this big object, right? It's just going to cast a little shadow on this one. This one, on the other hand, is going to cast a fairly substantial shadow on this one. But that's the inverse square law, is basically in effect, in the sense of the shadow is a reflection. As this gets closer, it gets bigger. As it gets bigger, it will shadow more. And you have to say not bigger by size, but bigger by thickness, mass. Mass is going to decide the shadow. So it's not so much how big you are, it's how dense you are with mass that will dictate how much shadow you create. Yeah, probably enough of an add-on.
And it's easy to see, after some mental effort, that the further the sun is away, the less in proportion of all of the particles are being taken out of the possible directions in which particles can come. The solar size appears smaller. And in fact...
Yeah, so he's basically saying that the more of these will get to this, the further away this goes. So the further away this goes, the more of these sideways lines that would be able to access this. So this, as this gets closer, it blocks more and more angles of trajectory that might hit this.
Inversely is the square of the distance. So there will therefore be an impulse toward the sun on the earth that's inversely is the square of the distance, and is the result of large numbers of very simple operations, just hit one after the other from all directions.
So again, he described them as hits, and yet he didn't think about what they were, right? I mean, gravity moves the speed of light. He should have thought of them as photons. You should know that photons, although they hit, they don't really hit. Okay, they impart directional information. This is the guy that came up with Feynman diagrams that basically illustrate the exchange of directional information between electrons and photons. And yet he's thinking of this as being some sort of rock you're throwing.
And therefore the strangeness of the mathematical relation will be very much reduced, because the fundamental operation is much simpler than calculating the inverse of the square of the distance. This machine does the calculating.
So did you hear that, all you detractors? That, you know, Feynman's basically saying that, look, if you have a model, you don't need math, because you can just use the model to model the math. You don't need to do all these formulas, because you can just calculate it by drawing the triangles.
These particles bouncing. Only trouble with it is that it doesn't work for other reasons. Every theory that you make up has to be analyzed against all the possible consequences and to see if it predicts anything else. And this...
Yeah, well, I mean, the problem is that, you know, by that, like I said, you can use that two ways, right? I mean, you can use that to try to disable the truth, or you can use that to defend. So yeah, it just kind of depends on what position you're in, but you have to do it carefully. It's critique, all right, is a dangerous weapon half done. You either do it right or it's dangerous. Let's put it that way. Your constructive criticism becomes destructive criticism by just being a little bit too sloppy.
Predict something else. If the Earth is moving this way, more particles will hit it from the front than from the back.
More particles. So again, these are things moving the speed of light. And again, so somehow these ones in the back are somehow escaping the speed of light. And what are they hitting inside? You know, that's again, I can't have, you know, I don't have the expectation that he would dissect matter, but I mean, he's a physicist. Isn't that what physicists, shouldn't physicists already know that there's like moving parts inside of matter? That it's not just stagnant stuff, that it's actually moving, and that if it's moving a velocity, that there's a consequence that those speeds would be additive, that you'd somehow have to account for adding them together, and that you can't go faster than the speed of light, and you'd have to explain velocity in those terms.
If you're running in the rain, more rain hits you in the front of the face than in the back of the head.
If I'm running in the sunlight, does that mean more sunlight hits me in the front than in the back? Obviously, I'd have to be going incredibly fast for that to be true, wouldn't I? And I'd have to be running in the direction that the sun is coming from, wouldn't I? If I was in an even pressure field, it wouldn't matter how fast I ran, would it? Theoretically? If it's all moving the speed of light in all directions, would it matter which direction I run in? Would I hit more stuff if I run in some particular direction?
Because you're running into the rain. And so as the Earth is moving in this direction, it's running into the particles, rather, and running away from the ones that are chasing it from behind. So that more particles hit it from the front than from the back, and there would be a force also sideways whenever there was any motion.
There would also be a force sideways whenever there'd be any motion. Well, see, sideways, I guess he means by sideways, it'd be a force, a friction, I guess, is what he's saying. But it's, you know, I don't think it was very articulate that way. I mean, obviously, I don't think there'd be any motion sideways. There wouldn't be resistance sideways to you running in the rain. The sideways wouldn't be bothering you any. I mean, it would be irrelevant.
Sideways force would slow the Earth up in the orbit, and it certainly would not have lasted the at least 4 billion years that it has been going around the sun.
Right, so we already had that as a given, right? We already know that the theory would have to account for that in some way. And he just didn't give it any chance to account for that. So, I mean, yeah, it's a real thing. You have to say, look, you have real... If you have a substance that's supposed to be doing something, you have to account for what it's doing and how it's doing it. So I thought of another way to describe it, and so I'll go to my drawing, I guess, and we'll do this. You know, a way to illustrate the force dynamic. So, but let's remember again that this is about the fact that if you think of it as a kinetic equation, so you just think of the thing going in a direction, and you think of a kinetic force that would be increased in the opposite direction, the opposing direction, okay? Because now you're increasing something's velocity. So there's a more likely interaction in this direct conflict. Your argument is as something gains velocity, it will now incur more force in the opposite direction. It will catch up to more stuff somehow and crash into it. And more of that stuff will be theoretically a force in the opposite direction. You're moving towards it, it's forcing in the opposite direction, and you're going in this direction. And so just as a net force equation, I mean, Feynman was very good at doing net equations, you know, understanding systems and saying, well, what's the overall in, out, okay, after 5 seconds? You know, and thinking about it in those terms. Well, what happens after 5 seconds? What went in, what went out of a system, instead of getting caught up in each millisecond where you could get distracted and not understand what must be happening, where the compensations must be. So the compensation for this directional issue is, if you think of it kinetically, you can understand, just say, well, what's the implication of one thing going this way against a force coming in the exact opposite direction in a kinetic exchange? Well, the implication is absolutely nothing. There's no resistance to velocity in the direction of your force. So if you're moving in a direction, there is no opposition to your progress coming from anything moving in this direction. So if you convert it all into just net forces, just take all the angles out and just have the net force, that you're going a little bit faster this way, and the force is, the opposition is coming at you a little faster this way, and turn into a kinetic equation, you can fast realize that, oh, that's right, two pool balls hit, nothing happens, nothing changes. It'll just go right through it. The velocity will find it irrelevant. It won't be an impediment to its progress. And it's sort of the backward implication of that is that you can't really move anything faster than the speed of light. So let's say this idea of, that atoms are made out of particles, say, moving the speed of light, you could sort of get the idea that one couldn't be going forward and then be going faster than the one chasing it. So it must spend less time, or it must not go in that direction. It must go in this direction or that direction or all the other directions, but it really can't be going in this direction when this thing's coming after it, right? Because it can't really go faster than a photon. So it can go at the same speed as a photon, but it can't go faster than the photon. So it's not like it can gain speed on it. It can't gain advantage on it. It can't jump ahead of it. So it can't really escape it. And so just intuitively you can sort of get that that's probably the compensation here, is that this lack of resistance to the exact opposite force is the compensation for the fact that you can't really escape something moving the speed of light by moving the speed of light in the same direction plus velocity. So you have to be going some other direction that can be converted into a forward direction. Alright, so that was a lot of an explanation, so I think I can do it with this visual that will explain it. Alright, so if you understand something's velocity, let's just say there's a plane, and then there's, velocity would be just a line in different directions, right? So something that has no velocity, let's just say it has these equal, so just pretend this is just equal. It's all equal in all these different directions. It has no velocity. Now if I give it a velocity in a direction, what's basically going to happen, we can just understand that, is just this line gets longer. And for this line to get longer, what has to happen? Well, what has to happen is these lines have to get shorter. So now all of these lines have now lost a little bit. That's what was compromised. To create more in this direction, you had to take something from this direction. So everything you gain going this way, you take from the stuff you're going that way. Alright, so that's one way to understand it visually. You can sort of get that you're just changing the center of gravity. In a sense, you're moving it forward, so these lines would be the same length, but you'd have to see that as a center of gravity change. But just as a visual, you can sort of get it, that this is sort of a vector and a representation of the net velocity in a direction, is the fact that we have proportionally more. Now I could just make all these arrows a little longer and make these shorter, but I think visually it's more understandable that this is the net direction. This is where it's going overall. It might be going a little this way and a little this way and a little this way and a little this way, but the point is it's net going in this direction, and it's doing it by this much. And so that would be the velocity. So as the velocity increases, this line gets longer and longer and longer. And these lines get shorter and shorter and shorter. And what's the implication of that? Well, the implication is now when this greater force that we're talking about, as you go faster, there's more stuff coming at you. Well, the problem is it has less to hit here in terms of creating a velocity in the opposite direction. So this is the only way it can have any friction, is that it has to create velocity in this opposite direction. It has to create lines that get longer in this direction. And it can't really create lines that get longer because there's less to hit. And we still have, because of the speed of light, we still have force coming up this way that's not entirely escapable. I mean, obviously this is escaping it, but these other directions are not escaping it. And so they're still refining, they're still adding force going forward. That's what I meant by when I talked about the gravity on Earth still having the ability to add those 16 feet a second. Well, they're adding those 15 feet a second by moving these lines up towards this line. They're creating more of this line by essentially making, like I said, I could have drawn this by just making these lines longer, but the idea is these directions still exist, and they're going to be refined into this net direction. So anything I add to them by hitting them and moving them more straight, more on this line, we would just put on here and then put these back to their position. So let's say I hit one of these lines, I move it this way. Let's just add that extra distance to this arrow and then just put this line back where it was. So that's basically what's happening. But in the reverse end, there's none of that's happening. So as this extra stuff comes down, it has less to hit here. It keeps missing. It keeps missing. There's less refinements it can make. So even though there's more of it, there's less of it. There's more coming, but there's less to hit. Therefore, less potential velocity in this opposite direction. Less ability to steal. Less ability to shorten these arrows. Alright, so the net balance is that you will not have any opposition to this velocity. The velocity is allowed to move forward freely because as the velocity exists, it creates less potential in the reverse direction, less potential to create direction in the reverse direction. So as it's got more potential in this direction, as it converts itself into more fact of this direction, it loses ability to be converted into this direction. And that compensates for the difference in what you might think of as the stream. But the other way of thinking about it is just thinking about it in those raw terms that nothing can go faster than the speed of light. That there is no, this photon doesn't actually go the speed of light plus, plus a velocity. No, it just represents, this line just represents how much time this entire mass of stuff spends going in that direction. That's all. It doesn't imply more speed. It's implying, what it's stating is that the mass itself spends more time going that way than it's spending going that way. But it's not saying it's going faster. Essentially, the internal parts are all going the same speed. They never go any other speed but the speed of light. So there's no way to add speed to it. There's only a way to add direction, to make more of this line and less of these other lines. So I think that's a good way of describing it, a good way of understanding it. So here's a guy who was big on connecting arrows, adding arrows, and he couldn't do this, though. He didn't do that simple understanding of net kinetic dynamics. And and instead got lost in some notion that matter is some hard thing, and you're going to break little pieces off by throwing rocks at it or something that required there to be an energy transfer rather than a direction transfer. So is that enough? So I mean, again, just sort of think about it. If I start converting this entire structure, suck it all up into one line going one direction, that's sort of like my school of fish analogy, that as matter is accelerated, all the mass of the matter will be going in one direction, all the fish will be swimming in one direction, and any thing coming this way they'll go right through, any obstacle coming in that direction. They'll just go right through it. And if they're moving the speed of light, it's irrelevant what's coming in this direction, because that always remains the same. You can't really, for everything it hits sooner because it's moving quicker, it missed something because it went past it before it got here. So for everything it got to before it left, okay, everything that it hit before it had time to get away, going out, it hit because it's moving faster. It hit early. So everything that gets here too early, something else will leave too late. So it just doesn't. That stuff you can't change, and that's another consequence of having a constant speed of light, and you can't exceed it. So every time it appears like you're exceeding it, every time it looks like something's moving faster than the thing chasing it, you have to realize there's got to be some compensation in the machinery that's making up for that, because that can't exist. It can't go faster than the speed of light, so something else must have its speed increase. Something going in some other direction has to have its speed increase. Something that has to have the time it spends in that other direction has to be increased for something to compensate for what would seem like something going faster than the speed of light. So less stuff has to be, like I said, in this bottom part, has to be susceptible to that change to compensate for what would be the inevitable obligation for something to go faster than the speed of light. You have to correct for the obligation that something move faster than the speed of light by saying rationally, well, there's got to be some reason it didn't, because it can't. And if it didn't, because it can't, it means something else did something else, which means something else moved in the direction of the velocity. Yeah, so I think that's enough of an explanation. So let's play a little more of this.
So that's the end of that theory.
So that's the story. That's the end of the theory. That's as much short shrift kind of thing. I'm not saying he didn't give it more thought than that. I'm just saying that that was the attitude. Okay, let's not try to make it work. Let's not think about it. Let's not work on it. Let's not tweak it. Let's not play with it. Now let's just dismiss it. And that's pretty much their attitude.
Well, you say that was a good one, though. It got rid of the mathematics for a while. Maybe I can invent a better one. And maybe you can, because nobody knows the ultimate. But up to today, from the time...
Yeah, maybe you can, and then, like I said, 30 years later, he basically said, I don't think he can.
Time of Newton, no one has invented another theoretical description of the mathematical machinery behind this law, which does anything else but say the same thing over again or make the mathematics harder.
See, I mean, that's just the attitude, right? It's just same old, same old. So we just say, oh, that's just same old, same old, same old, same old. And, what can you do? I mean, it's a brick wall, right? This isn't a scientist saying, let me hear it. No, it's somebody saying, nah, forget about it. I can't think of it. You can't think of it.
And at the same time doesn't produce some wrong phenomenon. I mean, they have, like this model does it, but it produces something which isn't true. So...
Well, it is true. So that's why you got it wrong. You got it wrong. You were wrong.
There is no model of the theory of gravitation today other than the mathematical form.
Right. And the video previous to this, the first lecture, he talks about velocity. I don't know if I'll bother playing those clips, but, and it says that nobody has an explanation for velocity. Obviously, this theory explains velocity. It explains time dilation and magnetism and fields and, magnetism and electricity. And it does go all the way down to the nuclear forces. It's just going to be a little more complicated diagramming all of that interaction. But again, the argument was always made that you can't use gravity because electricity and magnetism are so much more powerful a force than gravity. But it's only because electricity and magnetism are maximizing the effect of the force through polarization. So by having things sensitive to specific polarization of the gravity, you can magnify the gravity to any, whatever the density is, to its full density. So gravity is only taking effect, is only using some tiny portion of the potential of the gravity, because it's just exchanging directional information, where in the atomic nucleus it can be exchanging something a little more significant. And it certainly is more significant in that it's quanta, it's energy itself, on the scale of the atomic nucleus. So I'm just trying to think if there's a way I can to illustrate the point that you can make something much more effective. So it's like armor, it's like bullets, putting very hard materials, radioactive materials, on the tips of bullets to make them penetrate metals. It's the same kind of thing, right? You could fire 5 million of these regular bullets and nothing happens. But once you polarize a bullet, once you tip it, then it goes through the target and it means something. So now 90% or 99% of the value of the bullets is realized, where you're only getting 1% before, or 1/10 of a percent, or 1 to the minus 16%, or whatever the number would be.
If this were the only law of this character, it would be interesting and rather annoying. But what turns out to be true is that the more we investigate and the more laws we find and the deeper we penetrate nature, this disease, that every one of our laws is a purely mathematical statement in rather complex and abstruse mathematics. This is relatively simple mathematics. It gets more and more abstruse and more difficult as mathematics. And
abstruse. I never heard that word before. I don't know. I would say obtuse, but abstruse. Yeah, I have to look that up someday when I could care.
Why? I haven't the slightest idea why. It is only my purpose in this lecture to tell you about this fact. In other words, it's my purpose.
Yeah, okay, that's an all right attitude to have if you don't know an answer, but just this to dismiss the idea that there could be answers. That's what he's basically doing, and it's just that dismissal of the fact that this was a morass, that somehow there could never be a clarity to come out of it, and that you just and once you start doing this, once you start compromising clarity, you start talking about wave-particle duality, and you start opening the door to these contradictions, then it gets easier and easier to keep creating. Then you can start doing this spooky action at a distance thing and entanglement, and you'll start accepting all kinds of fudgy, inspecific, vague, barely any evidence for them at all, and you'll just start talking about it. It's like that's the answer. So I just think that's the decomposition of standards, and that was just a huge fault of physics, was for it to become so detached from mechanical models. I mean, physics started with mechanical models. People tried to model the solar system. They tried to model things. And then they just sort of gave up on a rational model, one you could understand, and decided to go with this abstract grouping of mathematical relationships for which there was no directly coherent geometry. So anyway, probably enough. I'll play a little more just since it's here.
In this lecture to explain really why I cannot satisfy you, if you do not understand mathematics too well, in trying to explain nature in any other way. It is the burden of this lecture, in fact, to just tell you the fact that it is impossible to answer honestly, the challenge of explaining in a way that a person can feel the beauties of the laws of nature without their having some deep understanding of mathematics.
Yeah, beauties of the laws of nature, deep understanding of mathematics. I'm not saying understanding mathematics isn't a good thing to do, but that just again sounds like religion, and I think that's the flaw there. So let's see if I can find the other Mahla Day video. Right? It's probably one of these tabs somewhere. Yeah, so this one, if I go back, that should take me here, and then let's just see what this one's about.
But the problem that you're asking, you see, when you ask why something happens, how does a person answer why something happens? For example, and when you explain a why, you have to be in some framework that you allow something to be true. Otherwise, you're perpetually asking why.
Okay, I think the question was is why magnetism, and so this was Feynman's explanation that it's, you know, that there's a chain of cause and effect, and first you have to establish what the premises are, and we just don't have the premises is the bottom line of it. But let's play a little more.
Ask, for example, why two magnets repel. There are many different levels. It depends on whether you're a student of physics or an ordinary person who doesn't know anything or not. If you're somebody who doesn't know anything at all about it, all I can say is that there's a magnetic force that makes them repel. But it's a...
Yeah, so that was another thing I wanted to get to, is it was, you know, in the other video he was always talking about the attraction, you know, when he was talking about gravity, attraction, and there was no, not even anywhere any indication that anything was pushed into something else. It was always that it was pulled into something. The Earth pulls the Moon, those kind of things. It was all a pulling force, never described as a pushing force. And that's sort of the irony here, is that I think it is a pushing force. All push, there is no pull. And the only time you have this idea of an internal push is because you have a lack of pushing in. Okay, it's only because you've taken a that's not the right way to say it. It's still a pushing force. It's always a push. Nothing attracts. Everything just gets pushed. And it's not a true push, but it's a change in directional information away. Never pulling towards. It's always changing away. So it's likely that the interactions that take place are only interactions where there's a deflection here. So something comes in, hits this, it leaves like this, and this goes up to here. So it moves this stick up one, so it changes this to this new position, changes this to this, and it leaves like that. So it's always a push kind of thing.
Force which is present all the time and very common and is in a basic force of almost, I mean, I could go a little further back if I were more technical, but at an early level I just have to tell you that's going to be one of the things you'll just have to take as an element in the world, the existence of magnetic repulsion or electrical attraction, magnetic attraction. I can't explain that attraction in terms of anything else that's familiar to you.
See, that's what we could do, though. We could, but he chose not to, because we could call it, you know, I mean, you know, the field lines of electricity and magnetism pretty much describe the pressure waves you get with motion in a medium. So wind would be sort of an argument you could make. They behave a lot like wind, so there are things you can compare it to. And it's just recognizing that if you take that comparison, that analogy, that metaphor, and just change it to fit the circumstance, which is the frictionless environment where no energy can be exchanged because its energy already exists. All the energy that exists already exists in the system. The universe is never, the universe can't get more energetic. It only has this much energy. The particles are the energy. And all you can do is change what direction they're realizing their energy in. If the whole universe decided to swim in one direction, you know, then you would get the idea that it's all just energy, and now it's going that way, and it just, you know, left. But that's all it is. It's all directional information.
For example, if we say the magnets attract like as if they were connected by rubber bands, I would be cheating you Because they're not connected by rubber bands, I shouldn't be in trouble. You'd soon ask me about the nature of the band. And secondly, if you were curious enough, you'd ask me why rubber bands tend to pull back together again, and I would end up explaining that in terms of electrical forces, which are the very things that I'm trying to use the rubber bands to explain. So I have cheated very badly, you see.
But it's not really a cheat. See, that's the thing, right? Because if you really think about it, it's about this idea of distance and motion. And the motion's all at the speed of light, and distance creates the illusion of time, and it's all about what happens and how much time is going to be what you perceive to be energetic. So anyways, probably enough. But yeah, I'll do more of these Feynman things. I mean, I really don't want to get. I mean, the rubber band explanation is a good explanation, but I don't know if it's. I don't want to get too far away from just getting this gravity thing established and the understanding of this basic function, and the fact that magnetism and electricity are just the same force with polarization added. So now you just create a hypersensitivity to the gravitons and of the right polarization, and then you create ones that other bodies are more sensitive to. So you magnify, quite literally magnify, the power of gravity to create electricity and magnetism. So probably enough of a video. This camera's fucked up. The battery went dead. I'm just trying to save it here. It's still fucked up. Alright, anyway. I need my camera. Anyway, till next time.